Hi everyone, this is Amine Chellali from Université Paris-Saclay. I'm going to present our work entitled Mentor-Guided Learning in Immersive Virtual Environments, the Impact of Visual and Haptic Feedback on Skill Acquisition. This work was co-authored with Flavien Lebrun, Cassandre, Assia, Boukezzi, and Samir Otmane. Traditionally, learners are trained in many skill acquisition tasks based on the mentorship model, where experts guide and supervise them. During the early learning stages, the experts' corrections contribute to improved skill acquisition. Here you can see in this video an illustration of the mentorship model during an anesthesia procedure. We observe that the mentor helps the student by providing feedback. This is referred to as augmented feedback to distinguish all the information provided by the experts to help the learner from that arising directly from the learner's perception of the task completion. The experts' augmented feedback can take different forms, and we can classify it based on the modality used by the experts to communicate it to the learners. They can, for instance, use the verbal modality to describe or correct the movement. They can use the visual modality by demonstrating the movement to the learners, or they can use the haptic modality by taking the learner's hand to correct their movements. Sometimes they can even combine several modalities at the same time to better convey the information. Mentorship is a well-established model for training technical skills, particularly in the medical field. However, it is not safe and not ethical because learners practice directly on real patients. This introduces some conflicting goals between the teaching outcomes and care efficiency. To overcome these limitations, immersive VR technologies have emerged as an interesting alternative. In fact, the learners can practice when they want on different scenarios and without hurting the patients. However, current immersive simulators are mostly designed for autonomous learning, where the novices practice on their own and cannot receive help and guidance from experts, thus breaking the mentorship model. So the specific problem we are tackling in this research is how to reintroduce the experts and their augmented feedback in an immersive simulator, and which modality or combination of modalities should be used to communicate with the learners. Among existing VR technologies, collaborative virtual environments emerge as an interesting medium. In fact, they can permit multiple users to work together in a shared immersive space, so they could be used to support interactions between teachers and learners. However, communication in collaborative virtual environments differs significantly from face-to-face communication in the physical world. For instance, visually demonstrating movement or physically guiding the learner's hand can be challenging to replicate in immersive collaborative virtual environments. In addition, as seen earlier, augmented feedback is often multimodal. Previous research in collaborative virtual environments has shown the benefit of combining modalities to improve collaboration. This raises interesting questions on how to design augmented feedback mechanisms to support interactions between experts and learners in these systems. This leads us to our research question. What is the impact of using unimodal and multimodal augmented feedback in an immersive collaborative virtual environment for transferring technical skills from an expert to a learner? Our general hypothesis is that the form of the augmented feedback will affect the learner's performance, cognitive load, and subjective learning experience differently. We will focus here in this work only on the visual and haptic modalities, as previous studies have shown that the verbal modality is less effective for learning technical skills in collaborative virtual environments. To investigate our research question, we conducted the following experiment. The objective was to compare the impact of using unimodal and multimodal feedback on learning to reproduce the optimal movement trajectory during a tool manipulation task. We recruited 27 participants in this between-subject study. They were divided into 3 groups according to the experimental condition. They were instructed to reproduce the optimal movement trajectory of a tool as accurately and quickly as possible. They also had to avoid some obstacles which display was controlled using a probe. The experiment was divided into 4 phases. First, all participants received instructions on the trajectory to reproduce. Then they had to reproduce this trajectory on their own to measure their baseline performance. After that, the 2 experimental groups were trained on the same task under the guidance of an expert, while the control group participants trained alone without feedback. Finally, all the participants performed the task again on their own to measure their performance after training. During the training phase, the visual group received feedback from the experts in case of error. It consisted of displaying an overlay of the expert's virtual hand over their hand to guide them visually towards the correct path. In addition to visual feedback, participants in the visual-haptic condition received haptic guidance based on the master-slave principle to correct their movement. The objective measurements included the accuracy of the trajectory, the time to complete the task, the number of crossed obstacles, and the number of the expert's interventions. The subjective measurements included the NASA TLX to measure the mental workload and the questionnaire to measure the quality of collaboration. We present here only the main results. The full results can be found in our paper. Regarding the trajectory during the training phase, the participants in the 2 feedback groups performed significantly better than the control group. There was no significant difference between them. On the other hand, the number of corrections from the expert decreased over time, but no significant difference was found between the 2 feedback groups. Comparing the pre-test and post-test performance, the results on the number of crossed obstacles show a significant main effect of the test and a significant main effect of modality on this measure. The participants performed better in the post-test than in the pre-test. In addition, the 2 feedback groups performed better than the control group. Regarding the quality of trajectory, the results show an interaction effect between the test and the modality. The 2 control groups improved their performance between the pre and post tests, while the control group performance remained stable. Regarding the mental workload, the results show significant lower scores in the visual-haptic group than the 2 other groups in 3 out of 6 dimensions of the NASA TLX. Finally, the results show that participants in the visual-haptic group felt a higher perceived behavior in the interdependence between their actions and that of the experts compared to the visual group. We summarize here our main findings. The participants were more accurate with feedback than without, which emphasizes the importance of guidance from an expert during the learning of new skills regardless of the feedback modality. This suggests also that the visual feedback is sufficient for tasks with dominant spatial components. In addition, the number of instructor interventions was similar and decreasing over time. This suggests that the learners started to gain confidence and to integrate the new skills. Finally, the multimodal feedback was more useful in improving user experience with the feeling of greater interdependence with the expert's actions and the lower mental workload. To conclude, our experimental task seems to be highly dependent on the visual cues, which can explain why adding the haptic modality did not improve performance. Future studies should investigate the impact of multimodal feedback on tasks with fewer visual cues to better understand its impact on motor learning. In addition, we observed a high variability in the participants' perception and acceptance of haptic feedback. Future studies should explore adding personalized feedback depending on the user's preferences. It will be interesting also to study the impact of augmented feedback on teaching with a focus on the teacher's perspective. Finally, it will be important to investigate the impact of augmented feedback on the long-term learning of technical skills and their retention. This will provide important insights into the design of immersive collaborative virtual environments that supports the mentorship model. This concludes this presentation, so thank you for your attention.